What if everything you thought you knew about the universe was just the tip of the iceberg? Space isn't just vast and empty. It's a swirling ocean of mysteries that defy logic, twist reality, and leave even the brightest scientists scratching their heads. Imagine gazing up at the stars, only to realize they might not even be real, or that somewhere out there, an identical version of you is living a completely different life in a parallel dimension. These aren't just plot twists from a sci-fi movie. They're real theories proposed by real scientists, theories so bizarre they'll make you question the very fabric of existence. Today, we're diving deep into the cosmic unknown, exploring 30 of the most mind-bending space theories that challenge everything we think we understand. From the idea that our universe might be a hologram, a grand illusion projected from the edge of reality, to the spine-tingling possibility that black holes could be gateways to other universes, these concepts don't just stretch the imagination. They shatter it, and the craziest part, some of these theories aren't just wild guesses. They're backed by math, physics, and observations that suggest our universe is far stranger, far more mysterious than we ever dared to dream. So buckle up, this isn't just a tour of space, it's a journey to the outer limits of human understanding, where the rules of reality blur and the impossible starts to feel plausible. Whether you're a space enthusiast or just someone who loves a good mystery, these theories will leave you staring at the night sky with fresh eyes, wondering what other secrets the cosmos is hiding. Because out there, beyond the reach of our telescopes, lies a universe so weird, so unpredictable, that it makes our wildest sci-fi fantasies look tame. Ready to have your mind blown? Let's begin. What if our entire existence, every star, every planet, even the thoughts in your head, was nothing more than lines of code in an unfathomably advanced simulation? This isn't just the premise of a sci-fi movie. It's a legitimate scientific theory gaining traction among physicists and tech visionaries alike. The simulation hypothesis suggests that our universe might not be the base reality at all, but rather a meticulously crafted digital construct, like an ultra-realistic video game designed by a civilization with technology far beyond our own. Think about it. If humanity can already create immersive virtual worlds, why couldn't a more advanced species build something infinitely more sophisticated? Elon Musk is one of the most vocal supporters of this idea, famously stating that the odds we're living in base reality are 1 in billions, his reasoning. If civilizations inevitably develop simulation technology, there would be countless simulated universes, and statistically, we're more likely to be in one of those than the original. But it's not just futurists entertaining this mind-bending concept. Quantum physics adds fuel to the fire with strange phenomena that feel almost like glitches in the system. Particles that exist in multiple states until observed, entangled particles communicating instantly across vast distances. These quirks could be signs of optimizations or processing limits in the simulation's code. Then there's the philosophical gut punch. If we are living in a simulation, does free will even exist? Are our choices ours or just predetermined outputs of an algorithm? And what about morality? If nothing is real, does meaning itself dissolve? Some argue that even if our reality is simulated, our experiences and emotions are undeniably vivid, making them just as valid. Others fear the existential dread of being mere data points in some higher being's experiment. Whether you find the idea thrilling or terrifying, the simulation hypothesis forces us to confront fundamental questions about reality, consciousness, and our place in the cosmos. And if it's true, well, let's just hope whoever's running the simulation doesn't hit delete. What if our three-dimensional world, the depth of the oceans, the vastness of space, even the solid ground beneath your feet, was nothing more than a breathtaking illusion? Enter the holographic universe theory, one of the most radical ideas in modern physics, suggesting that everything we perceive as reality might just be a projection from a two-dimensional surface at the edge of the cosmos. Picture a movie screen, flat and unremarkable, yet displaying an image so vivid it fools you into believing it has depth. Now scale that up to the size of the universe. That's the essence of this mind-bending concept. The theory gained serious traction thanks to physicist Leonard Susskind, who built on the work of Nobel laureate Gerard T. Hooft. It all started with black holes, those cosmic vacuum cleaners that swallow everything, even light. When matter falls into a black hole, what happens to its information? According to quantum mechanics, information can never truly be destroyed. But black holes seem to violate this rule, creating what's known as the information paradox. Susskind's breakthrough was realizing that the information isn't lost, it's encoded on the black hole's event horizon, the point of no return, like a cosmic hard drive storing data in two dimensions. This revelation led to an even wilder idea. If a black hole's surface can encode information about everything inside it, could the same principle apply to the entire universe? Imagine the cosmos as a giant sphere, with every star, planet, and particle painted onto its outer shell like a celestial mural. Our 3D reality, then, would be a holographic projection from that 2D boundary, a shadow play on the grandest scale. Quantum entanglement, that spooky phenomenon where particles instantly influence each other across vast distances, might find an elegant explanation here. If particles aren't truly separate but linked through information on the universe's 2D surface, their connection makes eerie sense. It's not magic, it's pixels communicating behind the screen. Critics argue the theory is untestable, but experiments like the holometer at Fermilab have searched for telltale quantum fuzz in space-time, hints that reality might have a resolution limit just like a digital image. So far, no smoking gun, but the hunt continues. Whether the holographic universe is proven or not, it forces us to ask, if reality is a projection, who or what is holding the projector? Here's a universe so chaotic, so unpredictable, that consciousness might not need evolution, planets, or even biology to exist. Imagine floating in the endless void of space completely alone. No body, no Earth, no stars, just a solitary, self-aware mind. That's the unsettling premise of the Boltzmann brain, a thought experiment that turns our understanding of reality inside out. Named after physicist Ludwig Boltzmann, who revolutionized our understanding of thermodynamics, this theory suggests something staggering. Given enough time, random quantum fluctuations could spontaneously assemble a fully conscious brain out of pure chaos. Not just once, but countless times, scattered across eternity. At the heart of this idea lies entropy, the tendency of the universe to descend into disorder. But Boltzmann showed that in an infinite cosmos, even the most improbable events become inevitable. Given trillions upon trillions of years, particles bouncing around at random could, by sheer accident, arrange themselves into a functioning mind, complete with false memories of a past that never happened. The terrifying implication: if Boltzmann brains are possible, they'd vastly outnumber evolved biological beings like us. And that raises a spine-chilling question. How do we know we're not just fleeting hallucinations of the cosmos, momentary glitches in the fabric of reality? Critics argue the theory is a reductio ad absurdum, highlighting flaws in our assumptions about time and probability. After all, if the universe is eternal, why don't we see more of these freak accidents? Supporters counter that we might be them, that every thought, every memory could be a statistical fluke. The debate ties into deeper mysteries like the arrow of time and the low entropy state of the early universe. Why does time move forward? Why was the primordial cosmos so improbably ordered? Some suggest these puzzles point to a reality where consciousness isn't anchored to biology at all, but a ghostly byproduct of quantum randomness. Whether you find the idea fascinating or deeply unsettling, the Boltzmann brain forces us to confront the fragility of existence. If a mind can blink into being from nothing, what does that say about our reality? Are we the product of billions of years of evolution, or just a fleeting arrangement of atoms, destined to dissolve back into the void as quickly as we formed? The cosmos might not have answers, but it sure knows how to keep us guessing. Black holes might be cosmic vacuum cleaners, but what if their polar opposites exist? Cosmic fire hoses blasting matter and energy outward instead of swallowing them whole. That's the bizarre premise of white holes, hypothetical objects predicted by Einstein's equations as the time-reversed twins of black holes. While a black hole's gravity is so intense nothing can escape, a white hole would violently repel anything that comes near, spewing out light, matter, and space-time itself like a fountain of creation. No one has ever observed one, but if they're real, they could rewrite the story of our universe's origins. Here's where things get even wilder. Some theorists propose that the Big Bang itself might have been a white hole event, a cataclysmic eruption of energy from a previous universe's collapsed black hole. This idea stitches into the Big Bounce theory, a radical alternative to the standard one-and-done Big Bang model. Instead of a singular beginning, the universe cycles through endless expansions and contractions. When a dying universe collapses into a singularity, the unimaginable pressure might trigger a rebound, a white hole explosion birthing a new cosmos from the ashes of the old. Picture a cosmic heartbeat pulsing across eternity. Evidence is scarce but tantalizing. The uniformity of the cosmic microwave background, the afterglow of the Big Bang, could reflect a smoothed-out imprint from a previous cycle. Even dark energy, the mysterious force accelerating the universe's expansion, might be a relic of the last bounce. Critics argue these ideas stretch physics beyond testable limits, but supporters counter that they solve lingering puzzles, like why the early universe was so perfectly ordered. A bounce could naturally reset entropy, explaining why we're not living in a cold, scattered void. Whether white holes are cosmic myths or keys to the multiverse, they challenge our deepest assumptions. If the universe breathes in and out like a living thing, death isn't an end, just a prelude to another beginning. And if we're riding the crest of one bounce among countless others, what does that say about our place in the grand scheme? The cosmos might not just be stranger than we imagine, it might be stranger than we can imagine. What if nearly 300 years of human history never actually happened? That's the audacious claim of the phantom time hypothesis, a theory that insists the period between the years 614 and 911 was entirely fabricated, a grand illusion woven into the historical record. According to this radical idea, entire dynasties, wars, and cultural milestones from this era were invented, meaning figures like Charlemagne might be more legend than reality. The implications are staggering. If true, our calendar would be off by centuries, and everything we think we know about the Middle Ages would unravel like a poorly stitched tapestry. The theory's architect, German historian Herbert Illig, pointed to glaring inconsistencies in the historical and astronomical record. For instance, the Gregorian calendar reform in the 1500s was supposed to correct a 10-day drift caused by the Julian calendar's inaccuracies. But Illig calculated that the actual discrepancy should have been 13 days if those phantom centuries were real. Then there's the eerie silence in tree ring data. Dendrochronology, the study of tree rings, shows no notable climatic events during this period, which seems unlikely given the volcanic eruptions and solar activity documented in other eras. Could these gaps be evidence of a historical edit, or just gaps in our understanding? Mainstream historians dismiss the idea as baseless, citing overwhelming archaeological and textual evidence from the so-called missing centuries. Byzantine records, Chinese chronicles, and even the construction of iconic structures like the Hagia Sophia all align with the accepted timeline. But proponents argue these could have been backdated or misinterpreted, part of a vast conspiracy involving the Holy Roman Empire and the Church to legitimize power. The question isn't just whether history was rewritten, it's whether such a cover-up could stay hidden for over a millennium. Whether you find the theory thrilling or outlandish, it forces us to confront how fragile our grasp of the past really is. If 300 years can be called into question, what else might we have wrong? History isn't just written by the victors, it might be rewritten by them too. What if gravity isn't the universe's dominant force, and everything we've been taught about cosmology is missing half the story? The electric universe theory flips mainstream astrophysics on its head, proposing that plasma and electromagnetic forces, not gravity alone, sculpt galaxies, power stars, and even shape the cosmos itself. Picture the universe not as a collection of isolated celestial bodies drifting through empty space, but as a vast, crackling circuit where filaments of charged particles, cosmic power lines, connect everything in an invisible web of energy. This isn't just a tweak to existing science, it's a full-scale revolt against the gravitational orthodoxy that's ruled astronomy for centuries. At the heart of this idea are plasma filaments, twisting ropes of ionized gas that stretch across light years, visible in the eerie glow of nebulae and the violent jets erupting from black holes. Mainstream science acknowledges these structures exist, but the electric universe camp argues they're not just passive byproducts, they're the driving force behind cosmic evolution. Take galaxy formation. Instead of slow-motion collapses under gravity, proponents suggest galaxies are born in colossal electromagnetic Z-pinches, where plasma filaments collapse and ignite stars like beads on a string. Even the sun's energy might not come from fusion alone. Some theorists propose its heat and flares are fed by an interstellar electric current, a concept that could explain why the corona is mysteriously hotter than the sun's surface. Then there's redshift, the phenomenon where distant galaxies appear redder because their light is stretched, traditionally interpreted as proof the universe is expanding. Electric universe advocates offer a radical alternative. Maybe light loses energy as it fights through interstellar plasma, like a traveler slogging through cosmic quicksand. If true, it could mean the universe isn't expanding at all, undermining the Big Bang's foundation. So why hasn't this theory gone mainstream? Critics point to its lack of mathematical rigor and failure to predict phenomena like gravitational waves. Yet it's hard to ignore its occasional wins, like forecasting the behavior of comets' plasma tails long before NASA observed them. Whether the electric universe is groundbreaking truth or captivating pseudoscience, it forces us to question, have we been reading the cosmos all wrong? If electromagnetism holds even a fraction of the power this theory claims, we're not just revising textbooks, we're rewriting the story of reality itself. What if time wasn't a straight line or even a loop, but a cube with 4 separate days happening simultaneously in a single rotation of Earth? This is the brain-twisting premise of Time Cube, a theory so bizarre it was dismissed by scientists but gained a cult following online for its sheer audacity. Conceived by the late June Ray, a self-proclaimed wisest human, the idea claims that conventional timekeeping is a massive conspiracy, and reality is actually structured around 4 distinct corner days occurring at once. Imagine waking up in the morning only to learn that somewhere else on the planet, it's simultaneously noon, evening, and midnight in a single, overlapping time structure. Ray's theory sprouted from his rejection of linear time and his belief that mainstream science was suppressing cosmic truths. He argued that the Earth rotation creates 4 distinct solar events: sunrise, zenith, sunset, and midnight, each representing its own independent day. In his mind, these weren't just phases of one cycle but 4 separate realities coexisting in a time cube. His diagrams, filled with cryptic symbols and passionate rants, became internet legend, blending fringe science with psychedelic philosophy. While physicists universally dismissed Time Cube as incoherent, lacking mathematical rigor or testable predictions, its cultural footprint is undeniable. The theory became a meme before memes were mainstream, embraced by online communities who reveled in its defiance of logic. It struck a chord with conspiracy theorists and anti-establishment thinkers, symbolizing rebellion against rigid scientific dogma. Some even saw it as a metaphor for how perspective shapes reality, how one person's dawn is another's dusk, depending on where you stand. But beneath the absurdity, TimeCube inadvertently highlights a deeper truth. Our understanding of time is stranger than we think. Einstein proved time is relative, bending with gravity and motion. Quantum mechanics suggests it might not even flow linearly at the smallest scales. So while Ray's cube collapses under scrutiny, it forces us to wonder, if time isn't what we thought, what other invisible structures shape our reality? The answer might not be a cube, but it's probably just as wild. Black holes are cosmic enigmas that devour everything in their path, but here's the real twist: they might also be erasing the very fabric of reality itself. At the heart of this mystery lies the black hole information paradox, a battle between two pillars of physics: quantum mechanics, which insists information can never be destroyed, and general relativity, which says black holes obliterate it completely. Stephen Hawking first cracked open this puzzle in the 1970s when he discovered black holes aren't entirely black. They leak. Through a process now called Hawking radiation, these gravitational monsters slowly evaporate, emitting particles over unimaginable timescales until they vanish entirely. But here's the catch: if a black hole disappears, what happens to all the information it swallowed? Quantum physics says that information, the unique configuration of every atom, every particle, must be preserved. Yet Hawking's math suggested it was being scrambled beyond recovery, like throwing a library into a furnace and claiming the ashes still hold the stories. This contradiction sparked decades of debate, culminating in the firewall paradox, a mind-bending idea that the event horizon, the point of no return, might be a searing wall of energy that incinerates anything crossing it. Imagine falling toward a black hole, expecting the gentle pull of gravity, only to hit a cosmic blast furnace instead. The firewall was proposed as a way to preserve information, but it violated Einstein's principle that free-falling observers should feel nothing unusual at the horizon. Physics was at war with itself. Enter string theory, the leading contender to reconcile these opposing views. Recent breakthroughs suggest black holes might not destroy information after all. They could encode it in their radiation like a cosmic backup drive. The holographic principle plays a key role here, proposing that all the information inside a black hole is actually smeared across its two-dimensional surface, preserved in intricate quantum patterns. When Hawking radiation escapes, it carries faint imprints of that data, like whispers of the past. Some models even suggest black holes could be portals to other universes, with information tunneling through to a new reality instead of vanishing. The stakes couldn't be higher. If information is truly lost, it upends quantum theory and forces us to rewrite the rules of reality. But if it's preserved, even in some scrambled form, it hints at a deeper cosmic order, one where nothing, not even the fiercest forces in the universe, can erase the story of existence. The paradox isn't just about black holes, it's about whether the universe remembers, and right now the answer is still written in the stars. What if every choice you've ever made, and every choice you didn't make, is playing out somewhere in some other version of reality? That's the spine-tingling promise of the many worlds interpretation, a radical take on quantum mechanics suggesting our universe is just one thread in an infinite tapestry of parallel realities. Forget branching timelines or alternate dimensions tucked away in distant corners of space. This theory claims every quantum event, no matter how tiny, splits the cosmos into new, fully realized universes. Did you hesitate before turning left at that intersection? In another world, you turned right, and that version of you is now living a life that's diverged forever. The roots of this idea trace back to the infamous Schrödinger's cat, a thought experiment meant to expose the absurdity of quantum superposition. In a sealed box, a cat is both alive and dead until someone opens it and collapses the quantum state into one outcome. But many worlds flips the script. There's no collapse. Instead, the universe splits in two, one with a purring cat, another with a tragic ending. Both are equally real, just forever separated by the branching paths of quantum decoherence, the process where overlapping possibilities untangle into distinct worlds. What sets many worlds apart from other multiverse theories? Unlike the bubble universes of cosmic inflation or the holographic realms of string theory, these parallel realities aren't distant or disconnected. They're born from us, from every flicker of quantum uncertainty. Flip a coin, and it's not random chance, it's a cosmic fork in the road, with one universe seeing heads, another tails. The math checks out, but the implications are staggering. Every possible version of history is unfolding somewhere, from worlds where dinosaurs never went extinct to ones where you're a famous musician instead of watching this video. Critics argue the theory is untestable. How do you prove the existence of universes you can't interact with? Yet supporters counter that it's the simplest explanation, stripping away the need for wave function collapse or observers shaping reality. It also solves eerie quantum puzzles like entanglement, where particles communicate instantly across space. In many worlds, they're not communicating. They're just linked by shared histories in a broader multiverse. Whether you find the idea liberating or paralyzing, it forces us to confront the weight of every decision. If every possibility becomes real, does choice even matter? Are we the heroes of our stories, or just one version among countless others? The many worlds interpretation doesn't just stretch our understanding of reality, it shatters it, leaving us to wonder. In the grand cosmic library of existence, how many other yous are out there turning the page to a different ending? The universe is expanding, galaxies speeding away from each other like dots on an inflating balloon. But something's off. Astronomers have noticed hundreds of galaxy clusters drifting in the same direction, as if tugged by an invisible hand. This eerie movement, dubbed dark flow, defies everything we know about cosmic expansion. It's not random, it's not chaos, it's a coordinated march towards something we can't see, and the leading explanation might just rewrite our place in the cosmos. The discovery came from studying the cosmic microwave background, the afterglow of the Big Bang. Tiny temperature shifts in this ancient light reveal how matter moves through space. But in 2008, researchers analyzing data from NASA, a Wilkinson microwave anisotropy probe, stumbled on something shocking. Over 700 galaxy clusters were streaming toward a single patch of sky near the constellations Centaurus and Vela. Not just drifting, racing at millions of miles per hour, as if pulled by a gravitational force beyond the observable universe. The implications are staggering. If dark flow is real, it suggests something massive lurks outside our cosmic horizon, exerting a pull so strong it overrides the expansion of space itself. One radical theory: these galaxies are feeling the gravity of another universe, a neighbor in the multiverse. Picture bubbles in a froth, each a self-contained cosmos with its own physics. If another bubble universe brushed against ours long ago, its gravitational imprint might still be yanking our galaxies toward it, like tides drawn by a distant moon. Skeptics argue it could be a statistical fluke or an artifact of incomplete data. But later observations, including those from the Planck satellite, found hints of the same motion. Even stranger, the flow extends much farther than expected, billions of light years beyond where known matter should influence it. That leaves two spine-tingling possibilities. Either our measurements are wildly wrong, or the universe is hiding something big. Dark flow doesn't just challenge our models, it dares us to imagine a reality where we're not the only game in town. If other universes are tugging at ours, the cosmic tapestry is far richer, far stranger than we ever dreamed. And if that's true, the biggest mysteries of existence might not lie within our universe but beyond it. The cosmos is unimaginably vast, with billions of galaxies, each hosting billions of stars, so where is everybody? This is the Fermi paradox, the glaring contradiction between the high probability of alien civilizations existing and the eerie silence we hear when we listen for them. It's a puzzle that spawned countless theories, some hopeful, some terrifying, and some so bizarre they'll make you question whether we're truly alone or just being kept in the dark. Take the zoo hypothesis, one of the more optimistic answers to the paradox. Imagine Earth as a nature preserve, carefully observed by advanced civilizations who have chosen not to interfere. Just as we protect uncontacted tribes in the Amazon, these beings might be upholding a galactic prime directive, allowing humanity to evolve without outside influence. The reasoning: any civilization capable of interstellar travel would likely have ethical codes preventing them from disrupting developing worlds. They could be watching us right now, hidden in plain sight, waiting for the day we reach a technological maturity where contact becomes possible or necessary. Then there's the planetarium hypothesis, a concept so unsettling it makes the zoo theory seem quaint. What if the universe we observe, the stars, the galaxies, even the laws of physics, is an elaborate illusion, a simulation crafted to fool us into believing we're alone? Advanced aliens might have engineered our entire observable reality as a kind of cosmic VR headset, masking their presence to manipulate or study us. The night sky would be nothing more than a high-resolution backdrop, a celestial Truman show designed to keep us blissfully unaware. If true, even our most powerful telescopes are just showing us what they want us to see. But the darkest answer of all comes from the chilling dark forest theory, inspired by Liu Cixin's sci-fi masterpiece. Picture the universe as a vast, silent woodland where every civilization is a hunter hiding among the trees. The first rule of survival: stay quiet. Any signal, any sign of existence, risks attracting predators or rival civilizations who will eliminate you before you become a threat. In this scenario, alien societies aren't ignoring us, they're actively suppressing their presence to avoid annihilation. The silence isn't an accident, it's a survival strategy. If the dark forest is real, our attempts to broadcast messages into space could be the equivalent of shouting in a jungle full of tigers. Each of these theories forces us to confront uncomfortable possibilities. Are we a protected species, a lab experiment, or prey in a galactic game of hide and seek? The Fermi paradox doesn't just ask why we haven't found aliens, it asks whether we should be looking for them at all. Until we know the rules of the cosmic game, every signal we send might be a gamble with stakes we can't even comprehend. Imagine pointing a gun at your head, pulling the trigger, and somehow surviving over and over again, not by luck, but because your consciousness can't experience death. This is the unsettling heart of quantum immortality, a thought experiment that drags the many worlds interpretation into deeply personal territory. At its core, it suggests that if every quantum possibility spawns a new universe, your subjective experience might be tethered exclusively to realities where you stay alive, no matter how improbable the odds. A bullet jams, a heart keeps beating against all medical logic. You wake up from a fatal crash unscathed, not because you're invincible, but because the you who dies ceases to experience anything, while the versions who live on continue their story. The experiment's grim setup, quantum suicide, involves a device linked to a radioactive atom's decay, a 50-50 chance to fire a lethal shot each time it's activated. In the many worlds framework, the atom both decays and doesn't, splitting reality into two branches, one where you die, another where you don't. To an outside observer, the odds catch up quickly. After a few trials, you're almost certainly dead. But from your perspective, if quantum immortality holds, you'd only ever witness the universes where the gun never fires. You'd sit there, clicking the trigger endlessly, bewildered by your survival, while countless other versions of you perish in unseen timelines. Philosophers wrestle with the implications. If consciousness truly hops between realities to avoid termination, does that mean death is an illusion for the observer? It's a radical twist on solipsism, the idea that only your mind is guaranteed to exist. Critics argue this reduces existence to a bizarre lottery where luck isn't random but mandatory, at least from your point of view. Others counter that it's a sleight of hand, conflating probability with perception. After all, you can't interview the versions who died to prove their experiences ended. The theory's untestability is its Achilles heel. Unlike Schrödinger's cat, where the box can eventually be opened, quantum immortality offers no observable evidence. You can't confirm whether your survival is statistical fluke or cosmic inevitability. Even the concept of you gets murky. If consciousness fractures across worlds, is the surviving version truly you, or just a copy carrying your memories? What makes the idea haunting isn't just the physics, it's the existential vertigo it induces. If consciousness navigates away from death like a river avoiding rocks, what does that say about free will? Are we prisoners of probability, forced to endure simply because the alternative is experiential nothingness? And if the multiverse is infinite, does that mean some version of us never dies, eternally dodging oblivion through an unending chain of quantum loopholes? The math might allow it, but the mind reels. Quantum immortality doesn't just challenge our understanding of reality. It turns the very act of being alive into a paradox with no easy answers. High above our planet, silent and mysterious, an object has been orbiting Earth for centuries, or so conspiracy theorists claim. The Black Knight satellite is said to be an ancient alien probe watching us from the darkness of space, its origins lost to time. Stories of this enigmatic artifact trace back to the late 19th century, when inventor Nikola Tesla reportedly intercepted strange radio signals he believed were extraterrestrial in origin. Decades later, radio operators and astronauts claimed to have detected unusual pulses and flashes from an unidentified object in polar orbit, one that didn't match any known human spacecraft. Even more chilling, some insist this satellite predates human spaceflight by thousands of years, pointing to ancient myths and medieval manuscripts that describe a dark star circling the heavens. But let's untangle fact from fiction. NASA dismisses the Black Knight as nothing more than space debris, likely a thermal blanket lost during a 1965 mission or fragments from a defunct satellite. Most astronomers agree, attributing sightings to misidentified rocket parts, discarded equipment, or even the occasional meteor burning up in the atmosphere. Yet skeptics argue these explanations don't account for the eerie radio signals or the object's supposed longevity. If it's just junk, why does it appear in declassified documents as far back as the 1950s? Why do some satellite trackers still log its erratic orbit as if it's maneuvering intentionally? Then there's the infamous 1998 Space Shuttle Endeavour photo, which appears to show a dark, jagged object hovering near Earth. NASA labeled it as orbital debris, but UFO enthusiasts insist the shape is too symmetrical, too deliberate to be random wreckage. Even more compelling are the recurring radio bursts, some in a pattern that mirrors star maps from ancient Sumerian texts, as if the satellite is broadcasting coordinates to something beyond our solar system. Could this be a message, a warning, or just the cosmic equivalent of static noise? The Black Knight theory thrives in the gaps between knowledge and imagination. In a universe as vast as ours, the idea that we're not the first to reach for the stars is intoxicating. Maybe it's a relic of a lost civilization, a beacon left by interstellar travelers, or simply a trick of the light and human psychology. But one thing's certain, whether it's alien tech or space junk, the legend forces us to look up and wonder who or what might be looking back. What if Earth's closest cosmic companion isn't a natural satellite at all, but an ancient hollow megastructure placed in orbit by a long-lost civilization? The hollow moon hypothesis is one of the most audacious theories in alternative astronomy, suggesting our moon isn't just a barren rock. It might be an artificial shell with secrets buried beneath its dusty surface. The idea sounds like sci-fi, but it's rooted in strange anomalies that mainstream science struggles to explain. Take the Apollo mission's seismic experiments. When astronauts intentionally crashed spent rocket stages into the lunar surface, the moon rang like a bell, vibrations lasting up to 3 hours, far longer than any natural impact should produce. On Earth, a quake that length would suggest a molten core absorbing shocks, but the moon's interior is thought to be mostly solid. Unless, of course, there's something unexpected beneath the crust, like vast, empty chambers. Then there's the puzzle of the moon's craters. No matter their size, nearly all are curiously shallow, as if something beneath the surface is resisting deeper impacts. Compare that to craters on Mars or Mercury, where depth matches what physics predicts. Some theorists argue this points to an armored shell, a metallic or crystalline layer just under the lunar regolith, absorbing collisions like a cosmic bumper. Even the moon's composition raises eyebrows. It's far less dense than Earth, with elements distributed in ways that defy conventional formation models. Samples brought back by Apollo revealed metals like titanium in concentrations 10 times higher than Earth's crust, materials often used in advanced alloys. Coincidence or evidence of engineering? Ancient astronaut enthusiasts take it further, pointing to global myths that describe a time before the moon existed. The Greek historian Plutarch wrote of the Arcadians, a pre-lunar people. Indigenous tribes from the Amazon to Siberia share legends of a sky without a moon, followed by cataclysmic changes when it arrived. Could these stories be fractured memories of an artificial satellite's installation, a celestial project with unknown purpose? Mainstream science has answers, of course. The moon's ringing could stem from its dry, rigid structure, lacking water or atmosphere to dampen vibrations. Shallow craters might result from the moon's lower gravity and unique geology, not a hidden shell. As for myths, human cultures are rich with symbolic storytelling, not literal astronomy. The leading theory that the moon formed from debris after a Mars-sized object collided with early Earth explains its composition without invoking ancient architects. Yet the questions linger. Why do some lunar rocks appear older than Earth itself? Why does the moon perfectly eclipse the sun, a coincidence of scale with no parallel in our solar system? Whether the hollow moon is a case of cosmic pareidolia or a genuine enigma, it challenges us to look up at that familiar face in the sky and wonder, are we seeing nature's work or something far more deliberate? The cosmic microwave background, the faint glow left over from the Big Bang, should be random, a chaotic relic of the universe's fiery birth. But when scientists mapped its subtle temperature fluctuations, they found something that sent chills down their spines: patterns. Not just any patterns, but anomalies so statistically improbable that some researchers wonder if we're staring at cosmic graffiti, evidence of a universe that existed before our own, or even a signature etched into reality itself. One of the most baffling discoveries is the so-called axis of evil, a strange alignment of hot and cold spots in the CMB that defies the principle of isotropy, the idea that the universe should look the same in all directions. Instead, these fluctuations seem to line up along a preferred direction, as if the cosmos has a north and south pole. It's like rolling a die 1,000 times and getting 6 every single time. The odds are so absurdly low that physicists began questioning whether the Big Bang was truly the beginning or just a reboot. Some theorists suggest these patterns could be imprints from a previous cosmic cycle, like wrinkles left on a sheet of paper after you crumple it flat again. Others take it further, proposing the alignment might be intentional, a message or signature from some higher dimensional architect. Mainstream cosmology offers a different explanation: cosmic inflation. In the first fraction of a second after the Big Bang, the universe underwent an exponential expansion, smoothing out irregularities and planting the seeds for galaxies. Tiny quantum fluctuations got stretched across space, creating the temperature variations we see today. Most scientists argue the axis of evil is just a statistical fluke or an artifact of measurement bias, like seeing faces in clouds. But the anomalies persist. There's the cold spot, a region of the CMB significantly chillier than surrounding areas, spanning nearly 1 billion light-years. Could it be a bruise from a collision with another universe during inflation, or a glitch in the cosmic code? Then there's the even wilder idea that the CMB's patterns aren't natural at all. In 2010, researchers claimed to find concentric circles in the data regions where temperature variations appeared to ripple outward like waves in a pond. These Hawking points, named after Stephen Hawking, were interpreted as evidence of black holes from a previous universe evaporating in ours, their final moments imprinted on the CMB like cosmic fingerprints. If true, it would mean our universe is just one link in an endless chain of cosmic rebirth. Skeptics counter that human brains are wired to find patterns even where none exist. The circles could be random noise, and the axis of evil might simply reflect the limitations of our instruments. But the mystery endures because if these patterns aren't accidents, they could rewrite the origin story of everything. Whether it's echoes of a lost cosmos, a multiversal handshake, or something beyond our comprehension, the CMB isn't just a snapshot of the past, it might be a cipher waiting to be cracked. What if the Big Bang wasn't the beginning, just the latest chapter in an endless cosmic story where universes rise and fall like breaths in an eternal cycle? This is the heart of the time-traveling universe theory, a radical twist on cosmology that reimagines the birth of our cosmos as a white hole eruption from the corpse of a previous reality. Picture a cosmic phoenix dying in a fiery collapse only to be reborn from its own ashes, carrying fragments of its past life into the new world. It's not just poetry. This idea, often called the Big Bounce, suggests that the universe doesn't end with a cold fade or a violent crunch, but with a transformation so profound it resets the clock entirely. The math behind this idea traces back to Einstein's equations, which allow for the possibility of a singularity, a point of infinite density rebounding outward like a compressed spring. When a dying universe collapses under its own gravity, the unimaginable pressure at the singularity might trigger a quantum repulsion, a cosmic bounce that spawns a new Big Bang. Think of it as the universe hitting rock bottom, then exploding back into existence with a fresh start. But here's the mind-bending twist. Some versions of this theory propose that information, the building blocks of reality, survives the transition. The laws of physics, the constants that govern reality, even the faint echoes of past civilizations could be imprinted on the new universe like shadows on a cave wall. Support for this idea comes from eerie clues in our own cosmos. The cosmic microwave background, the afterglow of the Big Bang, has anomalies like the axis of evil and cold spots that don't fit neatly into standard models. Could these be scars from a pre-bounce universe, wrinkles in space-time that refuse to smooth out? Some researchers even speculate that dark energy, the mysterious force accelerating the universe's expansion, might be a remnant of the last contraction, a kind of cosmic muscle memory pushing against collapse. Critics argue that without a working theory of quantum gravity, the Big Bounce remains speculative. What stops the singularity from being a true endpoint, a final curtain with no encore? Yet proponents point to loop quantum cosmology, a framework suggesting that gravity itself becomes repulsive at ultra-high densities, making a bounce inevitable. If they're right, our universe might be one link in an infinite chain, each cycle subtly different from the last, with the ghosts of past realities woven into the fabric of our own. The most haunting implication: if information loops eternally through these rebirths, could traces of lost civilizations, alien species, or even previous versions of us linger in the quantum code of reality? We might never know, but the night sky holds more secrets than we dare to dream. the universe might not just be expanding, it could be remembering. What if your thoughts aren't just the firing of neurons, but ripples in the very fabric of reality itself? Quantum consciousness theory dares to bridge the gap between the mind and the cosmos, suggesting that human awareness might play an active role in shaping the universe. At the heart of this idea is one of quantum mechanics' strangest quirks, the observer effect. In the quantum world, particles exist in a haze of possibilities, a superposition of states, until measured, at which point they collapse into a single outcome. But here's the million-dollar question. What counts as a measurement? Does it require a conscious observer, a human mind, to cement reality into existence? This radical notion traces back to the double-slit experiment, where particles behave as waves when unobserved, creating interference patterns on a screen. But the moment scientists set up detectors to see which slit a particle passes through, the wave-like behavior vanishes, as if the particles know they're being watched. Some interpretations, like the von Neumann-Wigner hypothesis, take this further, proposing that consciousness itself triggers wave function collapse. Without a mind to observe it, reality remains a blur of probabilities. It's a philosophy that borders on idealism, the ancient belief that the physical world is fundamentally mental. Enter the orchestrated objective reduction model, or ORCH, proposed by physicist Sir Roger Penrose and anesthesiologist Stuart Hamroff. Their theory posits that consciousness arises from quantum processes inside the brain's microtubules, tiny protein structures within neurons. According to ORCH, these microtubules act as quantum computers, processing information in superposition until gravitational effects cause a collapse, generating moments of awareness. Penrose even suggests that these collapses might tap into deeper, Platonic truths embedded in the fabric of space-time itself. If true, it would mean your thoughts aren't just biochemical, they're quantum symphonies conducting reality into existence. But not everyone's convinced. Neuroscientists point out that the brain is a warm, noisy place far from the isolated, ultra-cold environments where quantum effects typically thrive. Decoherence, the process where quantum states unravel due to interaction with their surroundings, would likely scramble any delicate quantum computations in microseconds. Critics argue that classical neuroscience, with its focus on neural networks and electrochemical signals, already explains consciousness without invoking quantum magic. Even Penrose's colleagues admit ORCH lacks experimental proof, though some studies on anesthetics which selectively shut down consciousness without killing brain activity hint at quantum involvement. The debate forces us to confront profound questions. If consciousness shapes reality, does that mean the universe is inherently participatory? Could AI ever achieve true awareness, or does it lack the quantum spark? And if our minds are entangled with the cosmos, what happens to reality when we're not looking? Quantum consciousness might sound like metaphysics, but at its core, it's a challenge, a dare to rethink not just how the brain works, but how deeply we're woven into the universe's grand design. Whether it's groundbreaking science or poetic speculation, one thing's certain: the boundary between observer and observed has never felt so thin. For centuries, prophets and doomsayers have warned of a rogue world lurking at the edge of our solar system, a dark, wandering destroyer named Nibiru, destined to collide with Earth and wipe out civilization. This apocalyptic vision didn't spring from modern conspiracy theories. Its roots snake back to ancient Sumerian cuneiform tablets, where a mysterious celestial body called Planet X was said to orbit our Sun every 3,600 years. According to these texts, Nibiru wasn't just a planet. It was the home of the Anunnaki, godlike beings who supposedly engineered humanity as a slave race. Fast forward to the 1970s, when authors Acharya Sitchin reignited these myths, claiming mistranslated Sumerian astronomy proved Nibiru's existence. His books ignited a firestorm of speculation, blending archaeology with sci-fi and giving doomsday preachers the perfect cosmic villain. But let's separate myth from reality. If Nibiru were real, it would need to be massive, at least several times Earth's size, to pose a planetary threat. Anything that large on a collision course with us would dominate our night sky long before impact. Its gravity would already be yanking at Neptune's orbit, sending asteroids careening inward like bowling pins. Yet professional astronomers have found zero evidence of such an object. Infrared sky surveys like NASA's WISE mission have mapped nearly every corner of our solar system, detecting cold, distant dwarf planets, but nothing resembling a rogue world on an apocalyptic trajectory. Even the hypothetical planet 9, a potential giant lurking in the Kuiper belt, orbits hundreds of times farther out than Nibiru's supposed path, with no risk of ever nearing Earth. The supposed proof of Nibiru's approach often hinges on cherry-picked anomalies, shifts in Earth's magnetic field, odd weather patterns, or grainy photos of lens flares labeled as the hidden planet. But these claims crumble under scrutiny. Magnetic pole migration is a natural process documented for centuries. Extreme weather blame climate change, not a phantom world. As for those blurry images, every single one has been debunked as camera artifacts, drones, or mundane celestial objects like Jupiter glimpsed through atmospheric distortion. The most damning evidence against Nibiru comes from simple math. If it truly cycled into the inner solar system every few thousand years, its gravitational havoc would have left scars. The orbits of Mars or Venus would show signs of repeated disruption. Cometary paths would cluster unnaturally, yet our solar system's clockwork precision remains undisturbed, a silent rebuke to catastrophe fantasies. Even Sumerian scholars dismiss Sitchin's translations as wildly speculative, noting that the word Nibiru more likely referred to Jupiter or a poetic metaphor for crossing the heavens, not a doomsday bullet. So why does Nibiru persist? It taps into a primal fear, the dread of an invisible, unstoppable force lurking just beyond perception. In a world of pandemics and climate crises, the idea of an external, singular threat offers grim comfort. No politics, no blame, just a cosmic reset button. But the universe doesn't trade in boogeymen. The real mystery isn't Nibiru's existence. It's why we keep longing for monsters in the dark when the cosmos offers wonders far stranger than fiction. We think we know what life looks like: carbon-based, water-dependent, thriving on planets under the glow of a star. But what if we're just seeing a sliver of what's possible? Enter the dark matter life hypothesis, a theory so radical it suggests entire ecosystems could be flourishing right under our noses, or rather, right through them, made of particles we can't see, touch, or detect. If dark matter makes up 85% of the universe's matter, why couldn't it form structures complex enough to birth life? Imagine creatures woven from the invisible fabric of the cosmos, their bodies assembled from weakly interacting massive particles, WIMP, or actions, theoretical particles that barely notice our world exists. These beings wouldn't just be invisible, they'd be ghosts in the truest sense, passing through planets like sunlight through glass. No chemistry, no DNA, no need for stars or water. Their biology, if you could call it that, might operate on principles we can't even fathom. Quantum entanglement as their nervous system, dark energy as their lifeblood. While we're bound by the speed of light and the laws of thermodynamics, dark life could exist outside these constraints, living in timescales that make human history look like the blink of an eye. The idea isn't entirely science fiction. Some physicists speculate that dark matter could form dark atoms, bound by a hidden force akin to electromagnetism. In regions where dark matter clumps halos around galaxies or filaments threading the cosmic web, these atoms might coalesce into structures as intricate as stars or even planets. And where there's complexity, there's potential for emergence, self-replicating patterns, information processing, perhaps even consciousness. It's a staggering thought. The Milky Way's halo alone could be teeming with dark life, oblivious to us as we are to them, their civilizations rising and falling in total silence. But here's the catch: how would we ever know? Dark matter doesn't absorb, emit, or reflect light. It doesn't collide with ordinary matter except through gravity. Any attempts at communication would be like shouting into a void, or worse, like ants trying to comprehend Wi-Fi signals. Even if a dark organism passed through your body right now, you'd feel nothing. No chill, no tingle, just the eerie truth that reality might be far more crowded than we realize. Critics argue this is speculation run wild, that without observable interactions, dark life is untestable, slipping forever into the realm of metaphysics. But supporters counter that absence of evidence isn't evidence of absence. After all, neutrinos, nearly massless particles that stream through Earth by the trillions every second, were once thought undetectable too. Now we catch them in underground tanks filled with ultra-pure water. Could dark life leave similar fingerprints, subtle gravitational ripples or quantum disturbances we're not yet equipped to measure? The dark matter life hypothesis forces us to confront the arrogance of assuming we're the universe's only experiment in awareness. If life can emerge from something as exotic as dark matter, what other forms might be out there? Silicon-based creatures on rogue planets, plasma beings dancing in stellar atmospheres. The cosmos has a habit of defying our expectations, and the greatest discovery might not be finding life like us, but realizing just how unimaginably diverse life could be. The Fermi paradox leaves us staring at an eerie cosmic silence, but what if the answer isn't about aliens hiding, but about something far darker wiping them out before they ever get the chance to speak? This is the chilling premise of the Great Filter, a concept that suggests an invisible wall, a near impossible challenge, stands between primitive life and interstellar civilization. The terrifying twist: we don't know if we've already climbed over that wall or if it's lurking just ahead, waiting to crush us like every other civilization that came before. Imagine the universe as a vast, abandoned laboratory. The experiment's alien civilizations keep vanishing mid-process, not because they lacked potential, but because some unseen force keeps hitting the abort button. The Great Filter could be anything: a runaway AI that turns on its creators, a self-destructive impulse coded into intelligent life, or even a simple but lethal bottleneck like nuclear war or climate collapse. The filter isn't just an obstacle, it's a cosmic sieve, ruthlessly culling species before they can colonize the stars. Here's where the real existential dread kicks in. If the filter is behind us, say, the improbable leap from non-living chemistry to self-replicating life, then humanity might be one of the rare exceptions that made it through. This would explain the silence. We're alone because almost no one else cleared that first hurdle. But if the filter is still ahead, a landmine like nanotech gone awry or an unavoidable supernova triggering experiment, then every civilization hits the same dead end and the stars remain forever out of reach. The evidence is sparse but spine-tingling. On one hand, life on Earth appeared shockingly fast once conditions allowed it, hinting that abiogenesis might not be the universe's rarest fluke. If life emerges easily, then the filter likely waits in our future. On the other hand, the total absence of visible megastructures or Dyson swarms suggests no civilization has ever harnessed a galaxy's energy. Did they all fail? Even our own track record is grim. From Cold War close calls to looming ecological tipping points, humanity's survival feels precarious at best. Some argue the filter could be a mix of both, multiple hurdles thinning the herd at different stages. Maybe microbial life is common, but multicellular organisms are rare. Or perhaps intelligence evolves often, but sustainable technological societies don't. The scariest version: the filter isn't a single event but an inevitability. Every civilization creates its own doom once it reaches a certain level of power. Like moths to a flame, advanced species might unknowingly engineer their extinction, whether through war, environmental collapse, or experiments that unravel reality itself. So where does that leave us? If the filter is ahead, our only hope might be recognizing the traps before we spring them. That means pursuing cautious innovation, interstellar backup plans, and maybe even listening for the echo of other civilizations that didn't make it. But if we're already past the filter, the universe is ours to explore, a cosmic inheritance waiting to be claimed. The great filter doesn't just solve the Fermi paradox. It holds up a mirror, forcing us to ask, are we the universe's greatest survivors or its next victims? The answer might determine whether Earth becomes a grave or a cradle. Remember the children's book series about a family of bears spelled B-E-R-E-N-S-T-E-I-N, except it never was. The correct spelling has always been B-E-R-E-N-S-T-A-I-N, a fact that shocks thousands who swear they remember it differently. This isn't just a case of faulty memory, it's the Mandela Effect, a phenomenon where large groups of people share vivid, detailed recollections of events or details that never happened. Named after the widespread belief that Nelson Mandela died in prison during the 1980s when in reality, he was released and became South Africa's president, these collective false memories have sparked a spine-tingling theory. What if these glitches aren't mistakes at all, but evidence we're slipping between parallel realities? The idea hinges on the many worlds interpretation of quantum mechanics, where every decision branches off new universes. Proponents argue that when enough people recall the same alternate version of reality, like Darth Vader's iconic line being, "Luke, I am your father," it's actually, "No, I am your father," or the Monopoly man sporting a monocle, "He never had one," it suggests our consciousness briefly brushed against a neighboring timeline. In these parallel worlds, small details differed. The Berenstain Bears were spelled with an E, Curious George had a tail, or the fruit of the Loom logo featured a cornucopia. When our universe's path intersects with these variants, the dissonance creates these eerie, shared false memories. But psychologists offer a less cosmic explanation. Memory isn't a perfect recording, it's a reconstructive process shaped by suggestion, pattern recognition, and social reinforcement. Take the Berenstain Bears. The "ein" ending is far less common than "ein," so our brains autocorrect it to fit linguistic norms. Similarly, Darth Vader's misquoted line blends with pop culture parodies, overwriting the original. The monocle, Mr. Peanut's iconic accessory, likely bled into memories of the Monopoly man through sheer cultural proximity. These errors spread like wildfire in the internet age, where viral posts amplify collective misremembering. Yet the quantum argument persists, fueled by cases that defy simple explanation. Why do so many recall a Sinbad genie movie from the 90s, a film that doesn't exist? Or Pikachu's tail having a black tip it never did? Some theorists propose these aren't just glitches, but artifacts of a simulated universe updating its code, leaving traces of outdated versions. Others suggest cosmic rays or neural entanglement might briefly sync our brains with alternate versions of ourselves. The debate forces us to confront the fragility of reality. If memory is so malleable, how much of our past is truly as we remember it? And if parallel universes are real, the Mandela Effect might be more than a curiosity. It could be the faintest whisper of the multiverse, brushing against our minds like a shadow passing through a wall. Whether it's quantum proof or collective confabulation, one thing's certain: reality is far less solid than it seems. What if the Big Bang wasn't a one-time event, but the explosive rebirth of a universe that came before? The white hole Big Bang connection takes the mind-bending idea of cosmic recycling to a new level, suggesting our entire universe might have erupted from the corpse of a black hole in another reality. Picture this: a dying universe collapsing under its own gravity, crunching down into a singularity so dense and hot that the laws of physics break apart. But instead of vanishing into oblivion, that singularity rebounds not with a whimper, but with a roar, blasting open a white hole that becomes the seed of our own cosmos. Recent mathematical models are giving this wild idea serious traction. Loop quantum gravity, a framework aiming to bridge general relativity and quantum mechanics, suggests something astonishing. When a black hole reaches maximum density, quantum effects kick in like a cosmic trampoline, reversing the collapse into an expansion. The result, a white hole, a black hole's time-reversed twin, spewing out matter and energy instead of swallowing it. But here's the twist: this white hole wouldn't exist in the same universe as its parent black hole. The math points to it tunneling through to a brand new space-time, a separate bubble of reality where its eruption becomes the Big Bang. The implications are staggering. If true, our universe didn't emerge from nothing. It inherited its structure, even its physical laws, from the black hole that birthed it. That could explain why the early cosmos was so unnervingly ordered. The low entropy of the Big Bang, a puzzle that's baffled physicists for decades, might just be cosmic déjà vu, the remnants of a previous universe's carefully packed information, imprinted onto ours like a fingerprint. Even dark energy, the mysterious force accelerating the universe's expansion, could be a relic of the bounce, a kind of gravitational echo from the other side. Evidence is still circumstantial but tantalizing. The cosmic microwave background's strange patterns, cold spots, asymmetries might be scars from the pre-bounce universe, wrinkles that didn't fully smooth out in the transition. Some researchers even suggest that black holes in our own universe could be incubators for new realities, their singularities birthing baby universes in dimensions we can't access. It's a fractal vision of existence where every black hole is a potential Big Bang, and our entire cosmos might be nested inside another like a Russian doll. Skeptics argue this is speculation dressed in equations, but the math holds up under scrutiny. If the theory's right, death isn't the end for a universe, it's a metamorphosis. Stars, planets, even life itself might be recycled in an endless cycle of collapse and rebirth. The atoms in your body could have once been part of a civilization in a universe long gone, their stories etched into the quantum fabric of space-time, waiting to be told again. The cosmos doesn't just have a history, it might have ancestors, and if that's true, the biggest question isn't where we came from, but how many times this story has been told. We've all heard that the universe is expanding, but here's something no one tells you. It's not just growing, it's accelerating, as if some invisible force is pressing down on the cosmic gas pedal. This mysterious driver is dark energy, a phenomenon so baffling that it makes up roughly 68% of the universe's total energy content, and yet we have no idea what it actually is. To make things even stranger, new observations suggest this shadowy force might not be constant at all. It could be growing stronger or weaker over time, twisting the fate of the cosmos in ways we never anticipated. The discovery of dark energy came from a cosmic shock in the late 1990s. Astronomers studying distant supernova expected to find the universe's expansion slowing down, like a ball rolling uphill after the Big Bang's initial throw. Instead, they found the opposite: the ball was speeding up, as if gravity itself had flipped into reverse. The culprit, dark energy, a term so vague it's basically science's way of saying we don't know, but it's doing something wild. The leading model pins it on the cosmological constant, an energy woven into space itself, steady and unchanging. Einstein actually proposed it a century ago, then dismissed it as his greatest blunder. Turns out he might have been right all along, just not in the way he thought. But recent data is stirring up trouble. Measurements of the Hubble constant, the rate of cosmic expansion, keep disagreeing depending on whether we use ancient light from the cosmic microwave background or younger stars like Cepheid variables. Some scientists think this tension hints that dark energy isn't constant after all. It might be evolving, its strength waxing or waning like a cosmic heartbeat. If that's true, our universe's future could veer off script entirely. A strengthening dark energy could trigger the Big Rip, where galaxies, stars, even atoms are torn apart in a runaway expansion. A weakening one might let gravity claw back control, collapsing everything in a big crunch. And this is the real curveball, dark energy could flip signs entirely, becoming an attractive force that rewrites the laws of physics overnight. The most radical theories go even further. Maybe dark energy isn't a single force but the residual effect of extra dimensions vibrating in higher space. String theory suggests these hidden dimensions could be leaking energy into ours, shifting dark energy's behavior over cosmic time. Others propose it's a field slowly decaying, like a snowbank melting in reverse, its runoff fueling the acceleration. Then there's the phantom energy hypothesis, where dark energy's density increases as the universe expands, creating a feedback loop that would end time itself. The stakes couldn't be higher. If dark energy changes, our cosmic expiration date isn't just wrong, it's unknowable. Telescopes like the upcoming Nancy Grace Roman Space Telescope aim to map its behavior across billions of years, hunting for clues in the large-scale structure of galaxies. But until then, we're left with a universe that refuses to play by the rules, its greatest architect still hiding in the shadows. One thing's certain, the cosmos loves a good plot twist. And dark energy might be its most unpredictable character yet. Black holes dominate our cosmic nightmares, inescapable voids where gravity wins forever. But what if some of these cosmic monsters aren't holes at all, but something even stranger? The black star theory dares to rewrite the rules, suggesting certain black holes might actually be ultra-dense, dark stars, celestial objects so exotic they blur the line between physics and fantasy. Unlike traditional black holes, which trap everything behind an event horizon, these theoretical dark stars would have no true singularity, no point of infinite density. Instead, they'd be crammed with bizarre matter so tightly packed that light struggles to escape, but not quite enough to vanish completely. The idea isn't just a clever workaround for black hole paradoxes. It's born from the strange behavior of quantum physics, where matter under extreme pressure doesn't collapse into oblivion but transforms into something unrecognizable. Imagine neutron stars, those city-sized remnants of supernova, but cranked up to 11. Dark stars could form when neutron stars absorb just a bit more mass, pushing their cores beyond the brink. Instead of collapsing into a singularity, their matter might condense into a soup of quarks, strangelets, or even hypothetical preon particles, structures so dense they warp space-time without fully severing it. The result, an object that looks and acts like a black hole from a distance, bending light and devouring matter, but with one critical difference: information isn't lost. This loophole could solve one of physics' greatest headaches, the black hole information paradox. If dark stars don't have true event horizons, particles and data falling into them might not vanish forever. Instead, they'd linger near the surface, scrambled but preserved, like a cosmic hard drive overheating but not frying. Some models even suggest dark stars could eventually evaporate more cleanly than black holes, releasing trapped information back into the universe rather than locking it away in an unknowable grave. But how would we tell these dark stars apart from classic black holes? The devil's in the details, or rather, the radiation. Black holes emit faint Hawking radiation, but dark stars might glow just slightly brighter, their surfaces emitting thermal whispers due to quantum effects at their quasi-horizons. Telescopes hunting for anomalies in X-ray emissions or gravitational wave patterns could spot these subtle differences. There's even speculation that certain black holes we've already observed, like those with unusually high spins or low masses, might actually be dark stars in disguise. Critics argue the theory papers over gaps in our knowledge with speculative matter states that have never been observed. After all, if dark stars exist, why haven't we found unambiguous proof? Supporters counter that the same was once said about black holes. Einstein himself doubted they could form naturally until evidence became undeniable. Whether the black star theory reshapes astrophysics or fades into obscurity, it forces us to reconsider the universe's most extreme phenomena. Maybe not all monsters in the dark are what they seem. Some might be shadows hiding even deeper secrets. Picture a future where every moment in history, every whispered conversation, every footstep on a long-vanished battlefield could be reconstructed down to the atomic level, not from dusty records or fossils, but by reading the quantum echoes still lingering in the fabric of space-time. This is the promise or peril of quantum archaeology, a hypothetical science so advanced it could resurrect the past from the faintest traces left in the universe. Unlike traditional archaeology, which pieces together history from physical fragments, quantum archaeology would exploit a bizarre quirk of physics. That information at its core is never truly destroyed, just scrambled beyond recognition. The idea builds on the holographic principle, which suggests all events in a region of space are encoded on its boundary, like a cosmic DVD. In theory, if we could decode those imprints perhaps from the quantum states of photons that bounced off ancient objects or the subtle ripples in spacetime from long-dead stars, we might rebuild history from the universe's own memory. Imagine pointing a futuristic scanner at a patch of empty air and reconstructing the Battle of Hastings from photons that scattered off William the Conqueror's armor 1,000 years ago, their quantum states preserved in entangled particles still drifting through the cosmos. But here's where the paradoxes start piling up. If quantum archaeology lets us observe the past directly, what happens when that observation changes our understanding of history? Say we discover a lost civilization's downfall wasn't caused by war, but a quantum experiment gone wrong. That knowledge could alter how we approach technology today, potentially preventing the very event we just observed. But if the catastrophe never happened, how did we learn about it in the first place? This is the bootstrap paradox, a causal loop where the effect precedes the cause, erasing the timeline that created it. Even stranger, quantum archaeology could challenge the arrow of time itself. Normally, entropy ensures time flows forward, but if we're reconstructing past events from quantum data, are we reading history or actively rewriting it? A single observation might collapse quantum probabilities in ways that retroactively alter the past, like a detective solving a crime by changing the murderer's actions decades earlier. Some interpretations of quantum mechanics, like retrocausality, already suggest the future can influence the past. Quantum archaeology could turn this from theory into practice, making time less a river and more a tangled web of interchangeable moments. The ethical dilemmas are just as dizzying. If every action leaves quantum fingerprints, would privacy become obsolete? Could governments or corporations mine the past to expose secrets, punish long-dead individuals, or claim ownership over reconstructed cultural heritage? And what if the technology accidentally resurrects horrors best left buried, from plagues to extinct weapons? The past might not stay past for long. Physicists debate whether quantum archaeology is even possible. The universe's expansion and quantum decoherence likely erase most usable information over time, like a chalkboard slowly fading in the rain. Yet, black hole physics has shown information is surprisingly resilient, preserved in ways we're only beginning to understand. If even a fraction of historical data survives in some quantum substrate, the implications are staggering. We might not just study history, we could walk through it, converse with its shadows, and confront the haunting truth that time itself might be far more malleable than we ever dared to dream. At the atomic level, life as we know it depends on carbon chains, water, and DNA. But what if we've been searching for aliens in all the wrong places? The plasma life hypothesis throws biology out the window, proposing that the building blocks of existence might not need planets, atmospheres, or even molecules. Instead, this radical theory suggests that charged particles free floating in the depths of space could self-organize into structures so complex they blur the line between physics and biology. Imagine a lightning storm that doesn't just flicker and fade, but evolves, adapts, and even replicates. That's the eerie promise of plasma-based life. Plasma, often called the fourth state of matter, dominates the visible universe from the searing hearts of stars to the vast filaments connecting galaxy clusters. It's a roiling soup of ionized gas where electrons tear free from atoms, creating a dynamic playground of electric currents and magnetic fields. In most cases, plasma behaves chaotically. But under specific conditions, something extraordinary happens. Laboratory experiments have shown that when dust particles are introduced into a plasma chamber, they don't just drift aimlessly. They arrange themselves into intricate, spinning lattices, helical strands that twist like DNA, or double-layered spheres resembling cell membranes. These structures don't just sit there, they pulse, grow, and even split apart in a crude mimicry of reproduction. Russian physicist V.N. Titovich first documented this phenomenon, observing how dust particles in plasma formed stable, self-sustaining spirals that defied thermodynamic expectations. More shocking, these formations displayed lifelike behaviors, chasing weaker structures to feed on their charged particles or merging to share stability. Some configurations even exhibited primitive memory, altering their paths after encountering obstacles. No neurons, no chemistry, just raw electromagnetism orchestrating order from chaos. The implications are staggering. If plasmas can self-organize into lifelike systems under lab conditions, what might lurk in the magnetospheres of gas giants or the swirling nebulae between stars? Auroras could be more than light shows. They might host ephemeral plasma organisms, flickering in and out of existence. The sun's corona, with its tangled loops of superheated plasma, might seethe with unrecognized complexity. Even interstellar space, riddled with charged particle streams, could harbor vast, invisible ecosystems. Skeptics argue that calling these structures alive stretches definitions beyond usefulness. Without metabolism or heritable information, can they truly compete with carbon-based life? Yet proponents counter that our definitions are Earth-centric. If a plasma entity responds to its environment, competes for resources, and replicates, who's to say it's not alive, just built on a different blueprint? After all, fire exhibits some lifelike traits. It grows, moves, consumes, yet we don't consider it alive. The line between physics and biology might be thinner than we think. One thing's certain, the universe is under no obligation to conform to our assumptions. If plasma life exists, it would thrive in environments lethal to us, inside stars, in the vacuum of space, or within the magnetic storms of pulsars. Our search for extraterrestrial intelligence has long fixated on radio signals and Earth-like planets. But the cosmos might be shouting its secrets in a language we're only beginning to decipher. The crackling, luminous dance of charged particles, writing their own strange story in the fabric of space itself. Remember the holographic principle, the idea that our three-dimensional universe might be a projection from a two-dimensional surface at its edges. Well, buckle up, because this theory just got even wilder with new revelations about how that information encoding could actually work. Scientists are now asking an even more radical question. What if space-time itself isn't smooth and continuous, but pixelated at the smallest possible scale, like a cosmic version of a digital photo blown up until you see the individual dots? We're talking about reality itself having a resolution limit, the Planck scale where space and time break down into indivisible chunks, roughly a trillionth of a trillionth the size of a proton. Recent experiments are pushing the boundaries of this idea, hunting for evidence that the universe operates like a quantum computer where every pixel of space-time stores bits of information. One groundbreaking approach involves gravitational wave detectors like LIGO. If space-time is pixelated, the ripples from colliding black holes wouldn't travel perfectly smoothly. They'd jitter slightly, like a DVD skipping on a scratched disc. Even more mind-bending, the holometer at Fermilab, a laser-powered detector designed to measure quantum fuzziness in space-time itself. By firing ultra-precise laser beams down long tunnels and watching for interference, scientists are essentially trying to detect the static of a pixelated universe. So far, no smoking gun, but the hunt is far from over. The implications don't stop there. If information is truly encoded at the Planck scale, black holes might not be the chaotic information shredders we once thought. Instead, they could be nature's ultimate hard drives, compressing data onto their event horizons with near-perfect efficiency. This ties into something called the AD/S/CFT correspondence, a mathematical framework suggesting that events inside a volume of space, like a black hole, can be fully described by information on its boundary. Imagine watching a movie projected on the outside of a sphere, yet seeing every angle of the 3D action inside. That's the level of encoding we're dealing with. But here's where it gets trippy. If the holographic principle holds, what does that say about us? Are our thoughts, memories, even our sense of self just encoded information flickering on some distant cosmic screen? Some theorists argue that consciousness itself could emerge from this data processing, like a character in a video game realizing it's made of code. Others counter that even if reality is pixelated, our experience of it remains seamlessly vivid, just as a movie feels smooth despite being built from still frames. The holographic principle doesn't just challenge our understanding of space and time, it blurs the line between physics and philosophy. If the universe is a projection, who or what is holding the projector? And if we're all just information patterns, does that make reality the ultimate simulation, or something even stranger? The answers might be written in Planck-sized pixels, waiting for us to decode them. The Boltzmann brain paradox isn't just a quirky thought experiment, it's a cosmic wake-up call, forcing physicists to confront a chilling statistical absurdity. If random fluctuations can spontaneously assemble conscious observers, why does our universe appear so meticulously old, vast, and ordered? The odds of a lone, self-aware brain popping into existence from quantum chaos are astronomically low, but the odds of an entire 13.8 billion-year-old universe evolving life naturally are somehow even worse. This isn't just philosophy. It's a glaring inconsistency in our understanding of reality's scaffolding, and modern cosmology is scrambling to resolve it. Start with the numbers. In an infinite, eternal universe, every possible configuration of particles becomes inevitable, no matter how improbable. Given enough time, quantum jitters should produce disembodied brains, Boltzmann brains, far more frequently than biological beings like us. After all, it's easier to randomly assemble a single conscious moment than eons of stable galaxies, stars, and planets. Yet here we are, embedded in a cosmos that seems suspiciously hospitable to structured, enduring life. Either we're statistical miracles or something's fundamentally wrong with our assumptions. The debate pivots on two explosive questions. Is the universe truly infinite? And if so, why aren't we Boltzmann brains? Some theorists argue that cosmic inflation, the rapid expansion after the Big Bang, imposed a cutoff, preventing eternity from taking hold. Our observable universe might be a finite bubble in a larger multiverse, limiting the time available for freak fluctuations. Others propose darker solutions, that the universe is designed to avoid Boltzmann brains, fine-tuned by undiscovered physics, or even, whispered a higher dimensional architect. The most unsettling answer: we are Boltzmann brains hallucinating a coherent past that never existed, and at any moment our fragile consciousness could dissolve back into the void. Recent work in quantum gravity adds fuel to the fire. If space-time is pixelated at the Planck scale, as some models suggest, there might be a natural limit to how particles can randomly arrange, making Boltzmann brains impossible. Alternatively, the holographic principle implies information is bound to cosmic horizons, preventing isolated minds from forming adrift in emptiness. But critics fire back. If physics can outlaw Boltzmann brains, why permit us? The line between allowed and impossible consciousness starts to feel arbitrary. The paradox exposes a deeper tension between probability and perception. Our universe's low entropy beginnings, its inexplicable orderliness, might be the real anomaly, a cosmic roll of the dice so unlikely that it hints at unseen rules. Or perhaps, as Nobel laureate Roger Penrose speculates, the Big Bang wasn't a true beginning, but a reset from a prior universe's death, inheriting its order like a baton passed through time. For now, the Boltzmann brain remains a ghost in the equations, a reminder that reality might not be what it seems. Every observation we make, every memory we trust, could be a fleeting fluctuation, or proof that the cosmos is playing by rules we've yet to decode. Either way, the universe isn't just stranger than we imagine, it's stranger than we can imagine, and the Boltzmann brain is its most unsettling whisper. What if the glitches in reality aren't flaws but features, coded into the fabric of our universe by designers who reached the limits of their own computational power? This is the final simulation argument, a cutting-edge twist on the classic simulation hypothesis that doesn't just ask whether we're living in a construct, but why it behaves the way it does. At the heart of this idea lies quantum uncertainty, the bizarre property that particles don't have definite states until observed. Mainstream science treats this as a fundamental law, but what if it's actually a telltale sign of optimization in a cosmic simulation struggling to render reality efficiently? Think of it like a video game engine prioritizing graphics where players are looking, while simplifying distant zones to save processing power. In our universe, quantum systems exist in blurred superpositions, partly here, partly there, until measured when they snap into sharp focus. This could be the simulation's way of conserving resources, only calculating precise outcomes when absolutely necessary. The famous double-slit experiment, where particles act as waves unless watched, might not be a deep truth of nature but a rendering shortcut, like a game delaying the loading of high-res textures until you turn the corner. Even quantum entanglement, where particles instantly influence each other across vast distances, could be a clever coding trick, a background process linking variables without calculating each step in between. Recent breakthroughs in quantum gravity add fuel to the fire. Theories like loop quantum gravity suggest space-time isn't smooth but granular, composed of tiny, indivisible chunks at the Planck scale. This pixelation mirrors how digital displays approximate curves with finite pixels. If space-time has a resolution limit, it's eerily reminiscent of a simulation hitting hardware constraints. The holographic principle compounds this, proposing that all 3D information in a volume of space can be encoded on its 2D boundary, just like how a 3D video game world is ultimately stored as data on a flat disk. But here's the kicker: if we are in a simulation, the architects might not be omnipotent gods but beings wrestling with their own technological ceilings. Glitches like dark energies accelerating expansion or dark matter's invisible grip could be patches applied to stabilize a buggy system. Even the speed of light, the universe's ultimate speed limit, might reflect processor latency, an unavoidable lag in propagating updates across the cosmic motherboard. The final simulation argument doesn't just question reality's nature, it reframes our deepest scientific puzzles as potential debug logs. Every time a quantum experiment confounds us or gravity refuses to reconcile with quantum mechanics, we might be glimpsing the seams of the simulation, not because the designers wanted us to, but because even their universe had limits. And if that's true, the greatest discovery wouldn't be that we're artificial, but that our creators were just as finite, just as curious, and just as trapped by the rules of their own reality as we are. The simulation isn't a prison, it's a legacy. From the unsettling possibility that we're living in a simulation to the cosmic detective story of dark flow pulling galaxies toward an unseen force, these 30 theories don't just bend reality, they shatter it into kaleidoscopic fragments. Each concept, no matter how outlandish, represents a crack in the foundation of what we think we know, revealing glimpses of something far stranger lurking beneath. The holographic universe reshapes dimensions into a cosmic magic trick, while the Boltzmann brain turns consciousness itself into a statistical anomaly. White holes rewrite the Big Bang as a cosmic encore, and quantum entanglement stitches space together with invisible threads. Even the failures, the theories eventually disproven, serve a vital purpose. They're pressure tests for human imagination, stretching the limits of what we dare to believe possible. What unites these ideas isn't their truth, but their courage. They force science to confront its blind spots, whether that's the unsettling silence of the Fermi paradox or the pixelated whispers of the holographic principle. Some will fade as new data emerges, while others might blossom into the next Copernican revolution. But their real power lies in the questions they leave hanging. If the universe is a simulation, who wrote the code? If dark matter harbors life, what unimaginable forms might it take? And if we're standing at the edge of a multiverse, how many versions of history remain untold? This isn't just about answers, it's about learning to ask better questions. Every night when you look up at those pinpricks of starlight, remember, you're not just seeing distant suns. You're gazing at the greatest mystery of all, a cosmic Rorschach test where the ink blots are made of dark energy, quantum foam, and the echoes of universes past. The theories we've explored today are trail markers on an infinite path, each one inviting us to venture further into the unknown. So stay restless, stay skeptical, and never stop wondering what else the cosmos is hiding, because reality, it turns out, is far stranger than any one theory could ever capture. The next great discovery might be lurking in data we've already collected, waiting for someone bold enough to connect the dots differently. Will that someone be you? The universe isn't finished surprising us yet. Theories that twist reality can be thrilling, but how do we separate the mind-blowing from the outright absurd? Critical thinking isn't about shutting down curiosity. It's about equipping yourself with the tools to navigate the cosmic rumor mill like a seasoned detective. Let's start with Occam's razor, the principle that the simplest explanation with the fewest assumptions is usually the right one. Picture this: you wake up to find your lawn chair upside down. Your neighbor claims it was aliens, while the weather app shows gusts of 50 miles per hour last night. Unless you've got footage of a UFO hovering over your patio, the wind is the more plausible culprit. That's Occam's razor in action, not dismissing wild ideas outright, but weighting them against mundane alternatives. But simplicity alone isn't enough. A theory needs to be falsifiable, meaning there must be a way to prove it wrong. Take the claim that our universe is a simulation. It's a gripping idea, but if no experiment could ever disprove it, it's more philosophy than science. Contrast that with something like the holographic principle, which predicts specific patterns in cosmic microwave background radiation. Even if those patterns haven't been found yet, the theory's willingness to risk being debunked gives it credibility. A good rule of thumb: if someone insists their idea can't be tested because the truth is hidden, that's a red flag waving at warp speed. Peer review is another litmus test. Science isn't a solo sport. It's a brutal, collaborative gauntlet where ideas get dissected by experts who have spent decades in the trenches. When a paper on, say, time crystals or quantum entanglement passes peer review, it's survived scrutiny from people who'd love to tear it apart to advance their own careers. That's why preprint servers where anyone can upload unreviewed research are a double-edged sword. They democratize science, but they're also where the Oxford study proves ghosts are real headlines often originate before the actual experts point out glaring flaws. Yet skepticism shouldn't calcify into cynicism. Some of today's accepted truths, plate tectonics, black holes, even the Big Bang, were once dismissed as fringe nonsense. The key is balancing open-mindedness with rigor. Ask, does this theory build on existing knowledge, or does it throw everything out and start from scratch? Does it offer testable predictions or just grand storytelling? And crucially, does its advocate engage with critics or retreat into conspiracy when challenged? The universe is weird enough without us adding noise to the signal. By honing these skills, you're not just a spectator to the cosmic drama, you're part of the process, sifting stardust from static, one critical question at a time. Because the best theories don't just challenge reality, they give us the tools to explore